Hi there, Nick here, M0NTV, and welcome back to my shack and to part 2 of our deep dive into designing an L-match, impedance matching network. Thank you very much to everybody that watched part 1, loads of people actually, and lots of new subscribers as well, so welcome to the channel. It's good to have you on board. We're going to be building on that, so if you've not watched that one, I would suggest you perhaps go and watch that one first before you dive into this one. And apologies, this is going to be a monster. I mean, even by my standards, right? And I don't exactly produce small videos, short videos, but this is big even for my reckoning. But there's a lot of ground to cover here, and specifically, we're going to get into something, and I've managed to avoid saying this so far, and resist the temptation to stop this video when you hear these words, okay? Because I know these words strike fear into the hearts of radio amateurs across the globe, but we are going to have some fun with the Smith chart. Yes, you heard it right. And I can hear the collective weight of your heart sinking when I said those words, Smith chart, right? And some of you are thinking, how on earth can I use the words Smith chart and fun in the same sentence, right? Well, just hang on a minute, right? I'm not talking about big paper charts with little numbers around the outside and you have to squint and estimate in between them and draw lines and all that stuff, right? We're going to use some brilliant free online resources that do all the calculations for us, so it makes it much more easier. And what we're going to do is we're going to look at the examples we did last time, but we're going to see those same examples now on the Smith chart, so you can see what those calculations mean in reality in terms of our matching of impedances. And you can kind of see where we're heading a bit more when you see it like that. So we're going to have a little look at that. I am by no means an expert. There are some excellent tutorials online about using the Smith chart and understanding it. So, you know, if you want to dive a bit deeper into that, then go and check those out. Really, all I'm trying to do here is just present some ways that I find it helpful to think about this stuff and understand it so that I can practically take it and use it and build something with it. So that's why I'm sharing this stuff with you. But after we've done that, then I'm going to show you how to cheat. And that's really brilliant and much more intuitive, actually. Then we're going to dig into the big thing of how we match complex impedances. So not just purely resistive sources to resistive loads. What happens when you've got reactances there that you need to take into account? So I'm going to show you how to do that, to calculate it, but then I will show you how to cheat. And actually, the cheating bit is particularly useful in that respect because you can really see what you're doing, whereas when you're calculating it, it's just a bunch of numbers, really. But anyway, so the two things together is quite a powerful thing. So I'm going to show you all that. And finally, I'm going to show you what I did and what I actually built and the difference that that humble little L match made to my RF amplifier. So, gird yourself. Make a very big, very strong cup of coffee, and if you're ready, we'll begin. I hope you find something of interest here. I hope you enjoy. Well, there are several online Smith chart calculators and simulators available. I like this one the best, and this is the one we're going to spend most of the time looking at. There is another piece of software as well, which I will show you briefly. So this one is by Will Kelsey. So you'll find that at will-kelsey.com, and if you click on Smith chart, it'll take you to it. Essentially, you put in the frequency that you're working at here. So we're gone for 7 megahertz once again, and the characteristic impedance, which in our case is 50 ohms. You will then see down here a whole bunch of different components. We're only going to be concerned with the first 4. And then here's where we build up the system here, and the way it's designed is though the circuit that we are trying to match is a black box, so we're not really interested what's going on inside it. It's just that it's presenting a particular impedance to the outside world, and that is the impedance that we're trying to match. And here is the Smith chart itself. Now, if you've ever seen paper versions of Smith charts, they're far more complex than this. There's lots and lots of circles and lots of labels, numbers around the side, and you have to kind of draw lines and estimate in between labels and the rest of it. Fortunately, this does all the calculations for us. And again, I am nowhere near an expert at this stuff. There are some excellent tutorials on what the Smith chart is and how to use it. So if you're interested in digging a bit deeper, then I suggest you go and have a look at one of those. But really, I just want to give you a very brief overview of it, just so that you've got a handle on it, because we're going to use it in a minute to do some impedance matching. So essentially what it is if you look at these circles here radiating out from the right hand side, these are circles of constant resistance, which means anywhere you are on that circle will be the same resistance. So at the moment we're at 50 ohms right in the centre, which is where we want to be. This is where we want to end up when we've finished matching. And this line, this horizontal line that goes through the centre, this is the line of zero reactance. So if you're on that line, you will have a pure resistance. And you'll see this here, because at the moment we've got 50 plus 0. So there's no reactive part at all. But yeah, I could change that to 25. There we are. So that's 25 ohms, no reactance. But if we were to move on a circle, one of these circles up here into this area, above the line, we would be moving into the area of inductive reactance plus J. And if we were to move below this line, we would be moving into the area of capacitive reactance minus J. And let me just show you what that looks like. So let's put it back to 50 ohms again for a moment. So that's 50 ohms, no reactance is the bullseye, right in the middle. Let's say we had 50 ohms and 25 ohms of inductive reactance. That would look like this. Now actually these lines coming here, we're not going to be too concerned with these, but these are actually lines of constant reactance. So anything on this line will have 25 ohms of reactance, but we're not worried too much about these. Just concentrate on these concentric circles here. Now there are more. These are just the ones that are labelled, because you know there are as many circles as you want to draw really. But that would be 50 plus 25J. Now let's say we had, and on this particular simulator it's already got a plus. If you want a minus, you've got to put a minus in. So if we went minus 25J, that would look like this. So that's 50 ohms with a capacitive reactance of 25. Now if we had a capacitive reactance of 25, how would we move around? Well, that's where these components come in. So let's say we had a series inductor. Okay, so here we are, 50 ohms minus 25, let's say 100 nanohenries. Okay, you see we've moved up a little bit clockwise on this 50 ohms circle. Let's increase that a bit, 300. Yeah, moved a bit more. Alright, okay. 400. Bit more still. 550. You see what's happening? Now we're almost there. Now actually, if you go down here, you'll see where this point is. So here, point 2, which is the point that we're at here, dp2, you will see we're only just got a little bit. So I mean, that's practically 1-to-1, and if we look on here, it gives us an SWO of 1.02. So what you'll see then is, by adding a series inductor, we've moved up and clockwise on this circle of constant resistance. But what if we had, let's go back to having 0. Go back to the bullseye. Let's say we put a series capacitor in. Right. 100 picofarads. Oh, look at that! So now, when it comes to moving this way, oh no, let's give ourselves a fighting chance here. 700 picofarads. So you see what's happening now. We've gone down, we're going anti-clockwise around this circle of constant resistance. And that is what we can do. So if we use a series inductor, we will go up and clockwise, more correctly, around these series. And not just this one, wherever we are, and all these ones that are not marked, that's what we'll do. We'll go clockwise around this circle of constant resistance. And if we use a series capacitor, we'll go down, we'll go anti-clockwise around it. So we can move up and down. Cool. But that's not the really cool thing about a Smith chart. Because a Smith chart, of course, is a reflection of impedance. Because, and as we looked at 2 videos ago, you know, impedance is a complex thing, isn't it? With a pure resistive part and an imaginary reactive part. But as somebody once commented, yeah, impedance is a bit of a kind of glass half empty way of looking at things. That is to say, when we look at impedance, we're looking at how effectively our signal is being impeded, right? So, you know, what are the problems, what are the obstacles that are stopping our signal getting through? And the more impedance there is, the less signal gets through. But there is another way of looking at exactly the same data from the completely opposite perspective. The kind of glass half full perspective, if you like, which is to say, instead of looking and saying, well, you know, what is stopping our signal getting through, which is effectively what impedance is, we could ask how successfully our signal is getting through. You know, how well our signal is achieving the goal of making it through the circuit. And this is what is known as admittance. Now, I'm not going to hold forth in great detail on this at all, but just to say, this is the impedance chart. So we've got the circles of constant resistance here, but we can do something else with this chart as well. Let me just clear this away. Let's take everything off it. Now, we can show admittance. Admittance is the inverse of impedance. That is to say, admittance is 1 over the impedance. So it's just looking at the same data from the completely opposite point of view. And just as impedance has a real and an imaginary part, so does admittance. And admittance has a real part called conductance, and it has an imaginary part called susceptance. And so what you're seeing here, these pink circles are circles of constant conductance. And admittance is useful sometimes to look at situations from this opposite perspective. Why I'm showing you this now is because this is a different set of circles going the opposite way. You remember the other ones, the circles of constant resistance, go around like this. Well, these are going round the other way. They're emanating from the other end, if you like. But here's the cool thing. Just as we were able to move up and down on circles of constant resistance, so too we can do so on these circles of constant conductance. And the way we do that, last time we used series capacitors and inductors. This time we're just going to use parallel ones. So let's try a parallel inductor. And a parallel inductor, okay, yeah, also let's try 500. So you see what's happening. So, and this is a case of less is more, if you see what I mean. So the more I increase the parallel inductance, the less we're actually moving. But can you see, this parallel inductor is enabling us to move up and round anti-clockwise along this circle of constant conductance. And no prizes for guessing if we put a parallel capacitor down, what that's going to do. Look at that. So we're moving down and round clockwise round this circle of constant conductance. So let me just put these other ones back on again now. Okay, now it looks a bit of a mess here. Take the admittance labels off. But what you just need to remember is you've got these brown circles going here, circles of constant resistance, and you've got these, well, pinky, purpley circles of constant conductance. And of course, they intersect. And not just at the obvious intersections like here, because there are a lot more, they're intersecting in different places as well. And because we can move up and down on both of these circles, we can move around the Smith chart. And this is how we match impedances, by carefully choosing either a series capacitor, which will take us down and anti-clockwise on the circle of constant resistance, or if we used a parallel capacitor, it would take us down round on this circle of constant conductors. Whereas if we were talking inductors, if we used a series inductor, we would go up and round this circle of constant resistance, whereas if we used a parallel inductor, we would go up this circle of constant conductance. So we can move in 4 different ways, and that's incredibly powerful. Now, what I want to show you now is those last 2 examples that we did in part 1, and show you what they actually look like when you see it on a Smith chart. So you will remember in the last video in part 1, we did 2 worked examples that came from experimental methods and RF design of low pass and a high pass impedance match. And so we're going to look at both of these, and I want you to see now what we're actually doing and what that looks like on the Smith chart. So here is our low pass filter, and so I've got my frequency set to 7, characteristic impedance 50, and so we've got a 10 ohm source, and it's purely resistive, as we remember. So there's our 10 ohm source, you can see it over here. And so what we did is we added a series inductor, which was 455 nanohenries. Now look at that. That's what we've done. And interesting, isn't it? Because this is where we're getting to. We've gone up to here, yeah. So now what we've done is we added a parallel capacitor, which was 909 picofarads. Boom. Look at that. And that is what we did last time, but I didn't show you this because I didn't want to get into Smith charts at that stage. But that's precisely what we've done. So now we calculated it all and got those values, but that is precisely what we did. We went up there and we went down there. And now if you come down here, you can actually add a constant Q circle. So now we know what the Q is, because we calculated that as well. The Q was 2. And what this will do, it will show you where you can do a conversion that will give you a Q of 2. Now look at that. You will see here, we're on here. So that means that as long as we don't go outside this kind of I shape, then we'll be able to get, you know, the kind of bandwidth that we want or whatever with a Q of 2. So let's have a look now at the high pass filter. Okay, so we'll take this off. So we've gone back to 10 ohms, purely resistive again. Here's the high pass filter. So remember, we start the high pass filter then with a series capacitor, 1.14 nanofarads. So we'll change this to nanofarads, 1.14. Now look at this. You see, now we've gone the other way. Yeah, we've gone the other way. So instead of going up here and down to here, we've gone down to here, and it's this same circle of constant conductance that we're going to hitch a ride on, but we're going to go the different way, the opposite way. And then we have a parallel inductor here, and that is 568 nanohenries. So let's move this up so you can see it. 568 nanohenries. Boom! There we are. And so that is the high pass filter. And as I said, you know, the L match is about as basic as it can get. What you can do, of course, is you can have more components on it, and that's where you get pi's and t's. What you can, of course, do is you can stack these together, so you can have like a series stack of this, so you can have another parallel one. What you can also do here is you can also put a circle of constant SWR, so let's put 1.5, and you can adjust the frequency span. Now this will give you an idea about what the bandwidth looks like. So let's just say, well, no, this is plus and minus, so let's do plus and minus 1 megahertz. And so you will see, as we are on the high pass filter at the moment, you perhaps won't be surprised to see that the 1 megahertz above our megahertz, all of that fits in to 1.5 to 1 SWR, whereas below it we don't get as much there, and that's because this is a high pass filter, so it's going to pass the higher frequencies through more readily. And what you can do is, if you're in a situation where you're finding you just can't get the bandwidth, what you can do is restrict the Q. So if we restricted the Q here, say, to 1, it's here, that would mean we couldn't go outside of here. So you'd have to kind of come down here and go up another circle here and then come down here. So you could do it, but it would take more hops, if you like. But what that will do, because you're not going outside of this constant Q circle of 1, it will mean that you get a better bandwidth here as well. So you can kind of play around with that. But yeah, so that is what we are actually doing. Now, let's just clear this stuff off for a moment. The great thing, of course, about this, and I showed you how to do all of this properly. Let's put the frequency back to 0 for now, just so it's not so cluttered, is that, of course, I'm going to put that back to 2. You can cheat. And what I mean by that is, if we didn't do any calculations at all, nothing, right? We rocked up to this and we said, okay, well, I've got 10 ohms resistive, I want to match it to 50 ohms resistive. What do? Well, if I wanted to go the low pass route, I could say, well, let's stick an inductor in, make something up, you know, 100 nanohenries. Oh, that's going in the right direction, yeah. Well, it's a bit more. What, 400? Yeah. Oh, yeah, that's all right. That's looking pretty good. A little bit more, 450. Yeah, well, that's about all right, isn't it? And we know, of course, that ours is 455, but we could have got there just by guessing. Particularly if you already decided you wanted this Q of 2, then you could put that there and that can be your reference. And then we think, okay, well, I need a shunt capacitor now. What's it going to be? I don't know. 10 picofarads? No, that's not going to do it. 100 picofarads? Oh, yeah, we need a lot more than that. 500 picofarads. Oh, on the right lines. 1,000 picofarads. Oh, we've gone too far. Let's back up then. 900 picofarads. And as we know, the calculated value is 909. But you could just do that. And it would work, right? This is the thing. And that's why I love this Will Kelsey tool, because, and I'm going to show you another piece of software in a minute, which does the same thing, and it's more powerful actually. But it's so easy to just click on these things and to do them. And you can, you know, try doing multi-hops and all kinds of different things. You can have great fun having a look at this and seeing how they compare and how they work. So you can just cheat and do that. Right. Okay, now, the next thing I'm going to show you now is how to match complex impedances. Matching complex impedances using an L-match network. Okay, so what do I mean? Well, what I mean is, so far we've just been looking at purely resistive matches, 10 ohms to 50 ohms in our examples. But what if you haven't got a purely resistive source? What if you had a 10 ohm source with an inductive reactance, a plus 10J, Or, say, a 10 ohm source with a minus 10J, a capacitive reactance. How do you match that to your 50 ohm load? Well, the first thing you have to do, and let's assume we've got an inductive source. So it's 10 plus 10J. So an inductively reactive source. The first thing that we do is we temporarily ignore the reactance of the source, and we pretend it's zero, we pretend it's purely resistive, and we go and do exactly what we did in part 1, and we design our L-match network, high pass or low pass, as you wish. When you've done that, you will end up with something like this. So let's say we've got our low pass filter, and here is our familiar low pass filter. And yet, for a purely resistive source, that will work great. But we haven't got a purely resistive source, have we? So now we need to remember that actually, now we've designed it, sadly, because we've got plus 10J there, this is not going to work now in the way that it did before. Okay, so what can we do about this? Well, what we need to think about is what this source looks like. What I mean is, this 10 ohm resistive source with 10 ohms of inductive reactance looks really like this. It looks like a 10 ohm purely resistive source in series with a 10 ohm inductive reactance. Now it's important to remember as you see these here, this inductor doesn't exist in reality. This is all part of the source. I'm just expressing the two different parts of the impedance separately, the purely resistive bit and the reactive part there. So that's what it looks like. Well, hang on a minute, you think. If we've got effectively within the source 10 ohms of inductive reactance, we were going to be putting in 20 ohms of inductive reactance in series anyway as part of our matching network. We need that. Excess needs to be 20 ohms for this to work. So we were going to be putting in 20 anyway. Turns out now that actually we've already got 10 in series as part of the source. So can we do something about that? Well, yeah, we can. What we can do is we can use this little calculation here. Now, this is a bit of a proprietary thing that I use here. So I'm trying to avoid using excess in the wrong sense, really, because excess is the series reactance, and this doesn't change for a purely resistive match. This is the same. So we need 20 ohms of series reactance to make this match work. Okay, I'm talking about X add here, and basically X add is the amount of reactance that we're going to add into here, series reactance we're going to add into here to make this thing work. And what this is saying basically is the amount of inductive reactance we're going to put in here is simply excess, which is what we're told we need, 20, minus the 10 that we realise we add anyway, which is part of the source. Okay, so if we need 20 but we've already got 10, then it's quite simple. We just take the 20 minus the 10, right? And so that will give us 10 ohms. So let's just take those away, and that's the additional reactance that we put in. And if we do the calculation, So that will give us 227 nanohenries. So that will be the value of the inductor that we will put in. And this is known as the absorption method. So remember, this inductor here doesn't exist in reality, it's part of the source. But instead of putting 20 ohms of series inductive reactance to make this work, we're still putting 20 in actually, but we're only actually adding ourselves 10 because 10 is already in the source. And what we're doing is we're absorbing, that's why it's called this, we're absorbing this 10 ohms of inductive reactance within our matching network. So we're killing two birds with one stone, as the saying goes. We're doing the match that we want to do, but we're also absorbing this pesky reactive element that we have as well. So very clever. And that's the absorption method. What about the high pass? Well, let's take a different source now. So let's say we've got 10 ohms again, but let's say this time we've got minus 10J. So we've got a capacitive reactance at the source. It looks like this, really. It looks like a purely resistive source of 10 ohms in series with a capacitive reactance of 10 ohms. But look, it's happening again. We find, well, just a minute, we were going to be putting in 20 ohms of capacitive reactance in series to make this match work. Turns out we've already got 10 as part of the source. We can use the absorption method and absorb this into the matching network here. Again, we do the sum, excess, what we need. The series reactance, we want 20 ohms here. But we've already got 10 ohms, so we have excess minus that, and of course it's exactly the same. 20 minus 10 is 10 ohms. If you plug those in, so that's the additional one that we're putting in there, you rearrange the formula of capacitive reactance and it will give you 2.27 nanofarads. And if we clean it up, that's what it looks like. And so we've done exactly the same thing, only this time we've done it with a capacitor instead of an inductor because we started with a capacitive reactance at the source. Okay? Now, quick recap then. If we've got a source with a capacitive, a minus J reactance, and that's with a series capacitor, a minus J component, then we can use the absorption method because we can absorb this capacitive reactance in the capacitor that we're putting in here. And exactly the same if we've got a source with an inductive, a plus J reactance, in series with a series inductor, a plus J component, we can do the same. We can absorb this inductive reactance as part of the inductor that we're going to put in our matching network here. But what if we've got a source with a capacitive reactance, a minus J, but we've got a series inductor? If we were using a low pass filter, but we had a capacitive reactance at the source. So we've got a minus J here, but we've got a plus J here. Or what if, the other way around, what if we had an inductive reactance as part of the source, but we were using a high pass filter and we were going to a minus J capacitor? Again, there's a mismatch there. Well, we can't use the absorption method for this. We have to use a different technique, which is called the resonance method, which kind of uses a little bit of the absorption method actually, but you'll see what I mean in a minute. So what's the resonance method? Well, let's assume we've got a source, and this is a high pass filter, as you can see here, the familiar high pass filter by now that we've been using. Let's say we've got a source with an inductive reactance. So we've got a plus 10J here, but we're going to be putting in a capacitor, right? So now we can't use the absorption method, right? Because we've got an inductive source here, but it's a capacitor we're going to put in. So what are we going to do about it? Well, first thing is to remember that our 10 ohms plus 10J source looks like a purely resistive source in series with a 10 ohms inductive reactance. Well, we know that. So this, again, is all part of the source. I'm just separating these two elements out. What we can do with the resonance method is, obviously we can't absorb this because this is a capacitor and this is an inductor. But what we can do is we can resonate it. And we can effectively null out this reactance by putting in series an equal and opposite reactance. So if we put in a capacitor with a capacitive reactance of minus 10J, that will null out the effect of this inductive reactance and give us 0 here, and then jobs are good 'un for the rest of the circuit, okay? So that would look like this. So that would work fine. But let's have a look. We can simplify this a little bit further here, and this is where we're getting into a little bit of the absorption method on this section. Right? This is the resonating bit here, putting this capacitor in, but now we can look at these two capacitors and say, well, actually, you know, we could do something here, because what we've got here, now we note here, this is not subtraction, this is addition here, because we're doing something different here, because this is the 20 ohms, the excess that we need to do our impedance match. But this is an additional 10 ohms of reactance that we need, because we need this 10 to cancel out the 10 ohms of inductive reactance in the source, right? So, you know, it's not like in the last two examples where we minused it. We need to add it now, because we've got to make up for this equal and opposite reactance that we're trying to kind of bring to resonance and null out. So this time what we say is we've got this 20 ohms of inductive reactance that we need to make our match, and we're going to add that to this X-res, this resonating reactance, to cancel out the reactance of the source. And when you do that, you get 30 ohms. Now we're going to come to this in just a moment, because this is where this can be a little bit counterintuitive. Because you might look at this and think, well, hang on a minute, if you've got two capacitors in series, you can't just add them, because capacitors in series are a little bit like inductors or resistors in parallel. There's a formula for calculating that. There is, but what you need to realise is that when we're talking about reactance, we're not talking about how many nanofarads or picofarads these capacitors are. We're not talking about their capacitance. We're talking about their reactance, and really, in that sense, they're functioning like frequency sensitive resistors, which is why we can get away with doing that. But just in case you're in any doubt about that, you could do it the other way, which is to say, we know we need to add an extra 10 ohms of capacitive reactance, and when you do the sums, that turns out to be 2.27 nanofarads. So we could do it based on the values of these capacitors. And so yes, there is a formula, and it's this. If we want to know what the total capacitance of these are, it's basically this one multiplied by this one divided by this one plus this one, which is what I've got here. And if you do the sums, that turns out to be 758 picofarads. Remember that, because you're going to see it in a moment. 758 picofarads. So you could basically replace both of those with one capacitor of 758 picofarads. Now, if we were to do it, I've got it there, but the original way, which was just don't worry about how many picofarads it is and just look at the reactance and plug that into your formula, 30 down here, and to find out how many picofarads you need, 758, right? So it works. It works both ways, whether you want to do it just based on the reactance, or whether you want to convert the reactance into capacitance. But then when you do that, you need to handle these capacitors as capacitors in the way that you calculate it. Right, okay. So to sum up, if you have a source with an inductive reactance and you're pairing that with a series inductor, you need to use the absorption method, which was the first one we looked at. Similarly, if you've got a capacitive reactance as part of your source and you're feeding that into a series capacitor, you need to use the absorption method. But if these are not matched, so if you've got like an inductive source going into a series capacitor, or a capacitively reactive source going into a series inductor, then you need to use the resonance method. And sometimes, as I said, you kind of use a bit of both to make it work. Okay, so how can we cheat at matching complex impedances? Well, actually, I think that this is where the cheating really comes in, because and in a sense it's not really cheating, but it's just more obvious what you're doing when you can see it. So let's take this example that we had then of the low pass filter. But let's say we had an inductive reactance of 10 ohms. So clearly that looks wrong. And we can see why. Because we were calculating starting from here, but we're further up on this circle of constant resistance. 10 ohms further up. So it stands to reason then, if you just look at that, you think, well, we've gone too far. All we need to do is just reduce this a bit. So, you know, 300. Yeah, us doing it. 200. Bit too far. 220, yeah. 35. 7. Something like that. And 1 to 1, right? And we haven't had to do any of that calculating at all. All we've just seen is seeing that we've gone too far. We need to pull it back, and you know, and that, of course, is the absorption method. Let's try another one. Put this one back to 455. Back to 0 for a moment. Yeah, so we're back to the normal resistive one. Let's say we have a capacitive reactance of 10. So now we can see again, we're not getting up to this point because we're starting down here. So clearly we need more. You know, we've got to get up higher to make that work. So last time we had to reduce it. This time we've got to increase it. So let's try 600. Oh yeah, not bad. 700. bit too far. Still a bit too far. Almost perfect, really. 1.01 to 1. Yeah. And as simple as that, you know. I mean, I spent all that time telling you how to do it properly. But this is what I mean. I think it's important to know how to do it properly because you understand now what we're doing. But it's very intuitive and easy to kind of do this kind of thing just on the fly like this. And so this is why I think this is such a really great tool to use. Now, the piece of software which was recommended to me is this piece of software called SimNEC, which is created by AE6TY. It is completely free, built on Java, so it runs on just about any OS you can think of, I think. So I'm obviously running it on a Mac. And it does very much what the Will Kelsey simulator does, but it does more. And to be honest with you, I've only been using this for a few days to figure my way around it, but it does a lot of things. You can save a lot of things as well. Same kind of thing. You can drag and drop, in this case, the components. So it works in a similar kind of fashion. What I do like about this is the graphing here. If we click on this, so what you can actually put, I'm not going to go into all the details here, but essentially this is SWR down this side, and this is graphing the SWR, but you can set the SWR limit as we did last time and the Q, but what we're seeing is what the bandwidth is below the SWR that you select, and it actually puts it down for you here. It's really brilliant. So this is the point of interest. This is 7 megahertz, but you'll see that actually between 6.182 and 7.717 megahertz we have an SWR of 1.5 to 1 or less. So that's pretty good, and you can actually see that. Now, I find this easier to look at than the one that Will Kelsey has on his. You know, when you kind of see the trail curl around and you have to try and get it in the circle. It's just another way of doing it, but I find this quite helpful because it looks more like what you'd see on the screen of a nano VNA or an antenna analyzer or something like that. So really very useful, and again, completely free, and there are some good videos and tutorials about using this particular piece of software as well. So I'm looking forward to kind of digging into this a bit more myself. But certainly worth a look, and I'll put a link to this in the video description. So finally, putting all this stuff into practice. Here is the RF pre-driver that I featured a few videos ago now, and you can see here, this is the input here. This is just the little DC blocking cap. So the actual port, the input port of the amplifier is here. And this is my L matching network. And you'll see I've got capacitance, series capacitance, and I've got parallel inductance, so you should know by now that that means this is a high pass filter. And you'll see this is a trimmer because I wanted some variability in this, because when you're building this, especially building it Manhattan like I do, there's all kinds of stray capacitance that you hadn't bargained on. So you can build it perfectly, but it still wouldn't be quite right because you can't model all this stray capacitance. So it's really useful to be able to adjust that. You can adjust the inductance, of course, by squeezing the turns together and pulling them apart a bit. Incidentally, don't do this. What I should have done is ripped this off and redone that, and so I should have, rather than push all those together, I should have put more turns on there and spread them out, because this produces stray capacitance as fast as you can look at it doing this. But anyway, do as I say and not as I do. But so this is it. Let me show you why I thought it necessary to build it. This is a screen grab from my Nano VNA, well, it's from the Nano VNA Saver software. And you'll see here I've got two markers. The red marker is set at the beginning of the SSB portion of the 15 meter band, 21.090, and the green marker is set at, well, pretty much the top end of the 10 meter band, 29.910 megahertz. So looking at the Smith chart, you'll see instantly that the 15 meter marker is below our zero reactance line, so we know that's a capacitive reactance, and the 10 meter one is above it, so we know that's an inductive reactance. And if we look at the SWR chart down here, I mean, it's not bad. The 10 meter one's pretty good, really. We've got a 1.2 SWR, but the 15 meter one was 1.6. I mean, it was all right, but I just wondered whether I could do any better. So that's why I built that matching L network. And so if you look at this here, this is the impedance as well here. So this one's up at 78 odd and this one's down here above 60 somewhere. The difference that it makes, so if you look at this here on the SWR chart here, now check this out. Look at that. And you can see instantly, I mean, look, this is the bullseye point, and these two now very close together, very close to the central 50 ohms marker. And look how flat this is. Now you can see clearly now why that it's a high pass filter, because look, the SWR skyrockets below about 15 megahertz, but is amazingly flat, you know, right through really to 50 megahertz and beyond. But over the bit that I'm interested in, superb. So I ended up with, well, almost 1-to-1, 1.04 to 1 at 15 meters, and at 10 meters 1.12 to 1. So really very pleased with that. And as I said, I didn't really need to do it with that, but I did it more as an experiment to see whether I could get it any better. So it does actually work and does make a big difference, that simple little L match. Well, to the two people still watching, well done, you made it to the end. I ought to give out medals really, shouldn't I? But apologies, it's been a long one. But I do hope over these past few videos you've found some useful information that you can take and do something with, and to build impedance matching networks in your own radios. Talking of own radios, the next video we're getting back to building mine, right? And I need to melt some solder and do some proper home brewing again, because I'm going to show you the power amplifier that is going in that 15 and 10 meter rig. That's for next time. Thank you once again for watching. Please like and subscribe, and I will see you on the next video. 73. Bye bye.